Hello and welcome back to this 28th lecture on bio microelectromechanical systems. Let's begin with a quick preview of what had been done last time. We talked about the flow over an infinite plate, okay, the way that the boundary layer would be created as a difference between the fully developed region of the flow and the layer adjacent to the plate which has a shear deformation. We talked about different types of flows regarding 1 to 3 dimensional flows and tried to calculate the velocity fields. We also discussed about a control volume dx, dy, dz and tried to ascertain or derive the conservation of mass equation, which is also the first Navier-Stokes equation. And then we did some solved examples for ascertaining the velocity component or the density with respect to time or space, okay, for compressible and incompressible flows. Again, to reiterate, compressible flows are those where density changes with time, incompressible where the density does not change as a function of time. So today we will try to derive the conservation of momentum equation, which is also the second Navier-Stokes equation. Essentially all this theory is very important because when we translate this theory to the micro scale, the interesting part is that the mass transport becomes time independent, okay, and that essentially also reveals why if there are two side by side flowing streams of fluid in a microchannel, they seldom mix owing primarily because of this reason. So if we look at how to derive the conservation of momentum, there seems to be something to do with acceleration of a fluid particle, because Newton's second law, force is nothing but mass into acceleration. So let us calculate first to begin with what is the acceleration of a fluid particle in a velocity field, okay. So we calculate here the acceleration of a fluid particle in a velocity field. So given the field V as a function of x, y, z and time in space time, let us assume AP is the acceleration vector of a fluid particle. Okay. So we want to find out what AP is in terms of velocity. Let us say the particle P is moving in the velocity field as represented here above in equation 1, okay. So at time t the particle is at position x, y, z, let us say. So at t position of the particle, let us say, is x, y and z. And this particle has a corresponding velocity at that point in space at time t, which is represented by Vp at t equals V x, y, z t. Let us say it has a velocity at t plus dt which is represented as x plus dx, y plus dy, z plus dz, t plus dt, alright. So essentially what it really means here is that let us say you have this rectangular coordinate system with x, y and z components, and you have a radius vector r somewhere here at point P with respect to the origin O, and this changes to another point P dash and the new radius vector becomes r dash plus dr, r plus dr. So essentially this is the position at time t, this is the position as t plus dt, and the vector connecting these two are really the position vector that the particle has traversed from point P to P dash, alright, and it definitely is a function of x plus dx, right. So essentially this point here is x plus dx, that means the traversing of the particle in the x direction by an elemental distance dx, the traversing of the particle in the y direction while this path is being executed. So it is the three components of this path, okay, as the particle traverses dy, and similarly the traversing of the particle in the z direction as the particle traverses dz from point P to P dash, okay. They are at two different time instances, t and t plus dt. So if we consider or if we try to find out what is the change in velocity as the particle moves from P, let us say, to P dash here, the velocity dp dvp can be effectively written as the rate of change of the velocity vector p with respect to x times of dx plus dxp rather, because xp is the, let us say, the position vector or the x component of the position vector at of the particle p. So dvx dv vector by dx, that means the rate of change of velocity in the x direction of the particle times of dxp plus rate of change of velocity of the particle with respect to y times of dyp plus rate of change of the velocity of the particle with respect to z times of dzp, okay. And you have a time component here, let us say the time is varying with respect to t. So the rate of change of velocity vector of the particle with respect to t times of dt. So this is how the differential element of velocity dvp can be written from vp. So if we do differentiate this with respect to time, so we will have dvp vector with respect to dt is essentially the rate of variation of v with respect to x times of, and this is again spatial component. So it should have only, suppose your v vector here is comprised of three components u, small v and small w, therefore u really is differentiable only with respect to x and not in time, okay. That is how you basically represent the velocity vector, while at the position p the vector is invariant, time invariant essentially, okay. So so del v by del x times of dxp by dt plus del v by del y times of dyp by dt plus del v by del z times of dzp by dt is plus del v by del t is essentially what your rate of change of velocity vector of particle p with respect to t is, okay. So now as we know here dxp by dt is nothing but the velocity of the particle at in the x direction, dyp by dt is the velocity of the particle in the y direction, and dzp by dt is the velocity of the particle in the z direction. We can represent them by u, v and w, okay. So essentially the acceleration vector then, which is nothing but the dv p by dt, the rate of change of velocity vector of particle p with respect to t is nothing but u del v by del x plus v del v by del y plus w del v by del z. So mind you again why we did not use the chain rule here for differentiation by taking the derivative of dv by dx, because v is essentially at a certain time point t. Again let me just reiterate this point once more, v vector is the velocity at time point t, and it changes to the velocity at time point t plus dt later on, you know. So, this is essentially x, y, z and t, and this is related to x plus dx, y plus dy and z plus dz plus times of t plus dt, as can be represented here. So, once you have differentiated this vector with respect to x, the time component is automatically gone out, and therefore, as far as time is concerned, the differentiation of v with respect to x is independent of time. Okay. So, therefore, the first component is not differentiated with respect to time. The second component, of course, represents or is a representative of the position of a particle xp, and what we are doing here is dxp by dt, which means it is the instantaneous velocity of the particle in the x direction when it is at position p. Similarly, dyp by dt is essentially a representative of the instantaneous velocity of the particle in the y direction when it is resting at p, and so on and so forth. So, these are essentially nothing but u, v and w, right. So, v with respect to x has already been independent of t. So, it is a constant as far as differentiation with respect to t is concerned, and this right here is the new term which comes out, and xp can of course be differentiated with respect to t, and this gives the instantaneous velocity of the particle in the y direction, in the x direction at the point p. Okay. So, that is how this equation emerges of acceleration from, you know, the previous equation. So, acceleration of the particle therefore can be represented as u dv by dx plus v dv by dy plus w dv by dz. Let me just quickly rub this and write this again, and that is what the acceleration vector ap is. Okay. And then of course, there is a del v by del t, the velocity of v with respect to time t. Okay. That is how you have defined the acceleration. So, the fluid may be accelerated as it is convected into a region of higher velocity, and let us look at that. If suppose you have a rectangular block of fluid, what kind of forces that block will feel because of stresses which are taking place in the medium with respect to that control volume. And really, if you look at the type of deformations that such a small control element would have in a shearing stream, assuming the volume to be present somewhere in the stream, the kinematics of such a mechanism can be illustrated as shown in this particular figure here. So, this is the box at the very outset, present in a rectangular coordinate system. The volume element has a volume of dx, dy, dz. Okay. And essentially this is an infinitesimal element of mass dm, where rho is the density. We assume the density rho is to be constant here, it is an incompressible flow. So, rho dx, dy, dz essentially is the total mass of this small volume element. Let us call that dm, and it moves in a flow field. So, the number of deformations that such a, or the number of kinematic states that this kind of a block would have can be that the block is simply translated. That means this was really the initial position of the block and it changed to this new position here. So, this is simply translated motion. It may rotate, which means that the block actually essentially being integral in shape or not changing or losing its shape rotates at the same point. It may deform, which means that the block actually starts now changing its shape from a square to more like a parallelogram, okay, something like this, or it may actually deform linearly. This is the linear deformation. That means a cube will become a cuboid. That means because of volume continuity, if you increase the length of the block by pulling it together, the area of cross section will definitely decrease. So, there are 4 different kind of kinematic states that this block can have while moving in a fluid volume. One is translatory, another is rotary, as you can see here. Third is angular deformation, where you are actually trying to compress the block and make it from a square into a parallelogram, and the fourth is linear deformation, where you are actually trying to pull the block and trying to reduce cross section and increase length. Okay. Okay, so let us actually consider the first aspect, that is fluid rotation. Okay, how this small fluid element would be rotated. So let us assume that omega be the angular velocity of rotation. If you again recall, the rotation is actually this particular case where you have a block at one angle and one position, and it actually rotates about its own place, retaining the center, okay, and goes to a different location, or rotates to a different location. So let us assume angular velocity here by which it is rotating is omega. So omega will again have three components, omega xi, j and k, which means that these omegas have different axes in which they have independent rotations. Okay. So really how do you define the rotation in this kind of a case, that if you suppose have two mutually perpendicular planes like this, and you are rotating the planes all together, retaining the perpendicularity between them, that means the planes are not really deforming among its own with respect to each other, they are just keeping in the same angle and then trying to rotate, and the average velocity of rotation in this case would be nothing but the velocity of plane 1 plus velocity of plane 2 which is orthogonally placed by 2. Okay, that is how you ascertain the average velocity of rotation of average angular velocity of rotation of two mutually perpendicular line elements of the particle in each orthogonal planes. Okay. So obtain let us obtain a mathematical expression for this, and then it will be a generic expression because it can be later on translated to the case where the angle between the plane changes as the rotation goes on, which is also the case of shear deformation, okay, the third case. So let us actually look at that aspect. So let us consider that in this particular case you have a coordinate system, let us say x y, and we are just considering rotation only in two dimensional plane, and you have a block somewhere in position O. Okay, these are the two diagonals of the block, and the block kind of rotates now in a position where this basically this diagonals actually now come like this. Okay, and there is a new location of the box created because of this rotation, okay, of this manner, right. So basically you have the block placed at coordinates m, n, p, q, and now the new position coordinates become m dash, n dash, p dash, q dash. Okay. So it rotates about the center O. So really this rotation can be figured out in terms of two angles, right. The angle which plane 1, this plane is able to define while it rotates, and plane 2, that means this plane mq, which is able to define as it rotates. In other words, we can also consider the two diagonals which are perpendicular to these planes, and they have a fixed angular relationship with respect to the plane, and we consider the rotation of the two diagonals in order to consider the average velocity of rotation in this particular instance. So let us assume that and proceed. So you have a case where you have diagonals along intersecting at point O, and in the first instance and after rotation these diagonals change positions to the new value, okay, where the perpendicularity between the diagonals is maintained. It is a case of pure rotation. Okay. So let us call these with different names. Let this be OA, OA dash, and this be OB and B dash. Okay. And essentially these move to new positions A1, A dash 1, and B1, B dash 1. Okay. So the way that rotation vector would be defined is definitely related to the angles that these two planes would move in. So let us assume this angle to be delta alpha, this to be delta beta. Okay. And let us also assume that the amount of distance that this particular plane OA moves as it goes to A1 is delta neta, and the distance here, the corresponding distance here is about delta x. Okay. And essentially here again the distance that this position B1 is spaced from this position B is delta zeta. Sorry, let me just rewrite this a little more here. So, essentially as you know the diagonal has moved by delta beta. So, the position here was B before, this is B1, and the distance between B1 and B is given here by delta zeta. Okay. So, this is delta neta, the distance between A and A1, and the distance between B and B1 is given by delta zeta. All right. So, these are some of the presumptions that we make to find out the relationship between the angles and the velocities. Okay. So, one important point to be considered here is that the rotation of vector OA, okay, this particular line OA is due to a variation in y component of velocity. So, let us suppose this particular point O is having or is defined by a velocity vector v x, y, z and time t, where v in the x direction is given by u, okay, y v in the y direction is given by v, and that in the z direction is given by w. Okay. So, essentially let us say the small v here represents the velocity in the y direction. So, there is definitely going to be a change of this velocity from point O here in this particular region to point A. Okay. The velocity is different. So, if we assume that change to be delta v, this is small v, mind you, this is not the v vector here, delta v by delta x. Okay. So, we can assume that if suppose the velocity at O in the y direction were v 0, the velocity at A would be equal to v 0 plus delta v times delta x times of del v by del x times of delta x. Okay. So, this is the additional velocity which is coming in the by the variation of the y component of the velocity as you move from O to A in this particular rotation case. So, the angular velocity of OA is really given by, as we all know, the rate of change of angle, right. So, limit of delta t tends to 0, delta alpha by delta t. We assume that these 2 points A and A dash are placed by a time point, or they are placed in time by a difference of delta t. So, delta alpha by delta t is really the angular velocity omega OA at this particular instance of time, and therefore, this can also be represented by limit delta t tends to 0, and what is delta alpha really? It is equal to nothing but delta neta by delta x. We assume this to be the length of the arc, okay, this distance here which is delta neta to be the length of the arc, and we assume the radius vector to be delta x. So, really the angle delta alpha which it moves is delta neta here divided by the radius vector delta x. So, that is essentially delta alpha divided by delta t. So, let us now try to figure out what this quantity really comes in or becomes, or what is there a relationship between the rate of change of velocity, the y component of the velocity with respect to x as we derived here. Okay. So, delta neta again, if we look at closely, would be nothing but the differential velocity change of v as it goes, or the y component of the velocity as it goes from y O to A, which is nothing but del v by del x times of delta x, okay, divided by or into times of delta t, the time that it takes for this point to go from A to A1. So, delta neta, the distance that the point A covers in order to go from A to A1 is nothing but the differential change in the y velocity with respect to x times of delta x, that is, this is the change or due to which the velocity at point A here is different than the point O here. Okay. So, this change times of delta t, that is exactly what delta neta would be, the amount of distance that A traverses when it goes to A1 would be. So, if I put this value of, let us say this is number 2 and this is equation 1, if I put this value of delta neta from equation 2 to equation 1, let us see what the value of omega OA finally becomes. So, omega OA then in that case is limit delta t tends to 0 times of del v by del x times of delta x times of delta t by delta x, okay, divided by delta t, which is nothing but dv by dx. All right. So, this essentially is dv by dx into delta x into delta t is basically the delta neta value divided by delta x divided by delta t. So, this comes out to be dv by dx. So, surprisingly enough, the omega OA or the angular velocity of the arm OA comes out to be equal to del v by del x. Okay. So, the rotation really translates into a rate of change of y velocity with respect to the x direction. All right. So, if I do the same thing for the other component, that is the component of the diagonal which was initially in the y direction, we may need to ascertain what is the change in the x direction, or what is the change in the x velocity in the y direction as it goes along the y, what is the change in the x velocity as it goes, and that would essentially be the omega OB. Okay. So, let us derive that expression as well. So, the rotation of the line OB of length delta y. So, essentially it has become too crowded here, but you can say that this right here from here to here, this distance is delta y. Okay. And you can also say that this distance is delta zeta as we have indicated, and the angle moved is delta beta. So, there is a similar kind of relationship to describe omega OB, and you can write that as limit of delta t tends to 0 delta beta by delta t. Okay. And this can further be expressed as limit of delta t tends to 0 delta zeta by delta y by delta t, and further we have, let us say u were the velocity, the x velocity at the origin here was u, and here the velocity is rather in the opposite direction is let us say u0 plus du by dy times of delta y. So, you have let us say u is equal to u0 plus du by dy times of delta y, pretty much in the similar manner as we did it for the x variation. We are doing the y variation in this particular case. So, the del zeta in this case really is nothing but minus del u by del y. Okay. I am sorry, this is actually minus because it will be in the reverse direction. So, essentially this would be u minus u0 would be minus. Okay. As you see here in this figure, the u is in this direction, but the del u by del x, the differential because of this rotation is really in the opposite direction. So, the value here would be u minus del u by del x times of del y. Okay. del u by del y times of the delta y. Okay. So, that is what so this is opposite to the direction of the positive u that you have taken. So, now we are left with delta zeta equal to minus del u by del y times of delta y times of delta t, right. The amount of distance that b takes to move to b prime or b1, okay. And therefore, omega ob in this particular case would be nothing but minus del u by del y in a pretty much similar manner as we did before for the x component. So, therefore, we find out that the omegas really of the two arms of or the diagonals of the two arms are dv by dx and du by dy with a minus sign. Okay. So, this is a very interesting derivation that we will keep in mind at this time for proceeding ahead with the momentum equation. So, this is what the rotational component would do. So, anything related to shear which causes such a rotational component would essentially give you values in terms of dv by dx and minus du by dy. Now, let us look at what the fluid deformation would be. Okay. So, the case 2 is regarding fluid deformation. Let us just refer back to that particular diagram here. Fluid deformation really is this second case, angular deformation, as you can see. So, the element actually changes its shape from a regular square into a more like a it is a quadrilateral or a parallelogram basically. So, essentially what rhombus. So, essentially there is a relative angular change between the two perpendicular planes, they do not remain at 90 degrees as such as the fluid moves. Okay. So, let us actually calculate using mathematics what this angular deformation would be. Okay. So, angular deformation involves changes in angle between two mutual perpendicular planes, right, changes in angles between two mutually perpendicular planes in the fluid. Okay. So, you have x and y coordinates here, you have a square with two diagonals, and you are angularly deforming this in a manner so that the new shape that it assumes has the diagonals moved away from perpendicular to this new angular shape. Okay. So, essentially you are doing a deformation in the particular shape. Now, as you do that, what essentially you are doing is that there is a diagonal, let us say in the again the same OA, B, A dash, B dash direction, and these diagonals are actually now changing in the A1, B1, B dash 1, A dash 1 direction. Okay. So, here let us assume that we have two angles just similar to the supposition before made before in the last case, was delta alpha and delta beta. Okay. And let us also assume that the distance between A and A1 becomes delta neta, the distance between B and B1 as just as the last case becomes delta zeta. All right. We also assume another angle here gamma which is in between, which essentially is your delta gamma. All right. So, here what really delta gamma is, it is let's say this is gamma, is not the delta gamma, this angle is gamma, and any change in this angle is delta gamma. All right. So, the change in this angle delta gamma is nothing but and this change, mind you, is negative. The angle is decreasing as you go along with time. Okay. So minus delta gamma is nothing but delta alpha plus delta beta. Okay. And essentially, if you just divide the whole by delta t, assuming that this shape was at time instance t and this shape came at t plus dt. So there is a time interval of del t in between or dt in between. So you get minus gamma, delta gamma by delta t is equal to delta alpha by delta t plus delta beta by delta t. So taking limits on both sides, as delta t approaches 0, this whole expression becomes minus d gamma by dt equal to d alpha by dt plus d beta by dt. All right. So that is what angular deformation would really mean. As we already know from earlier derivations, that delta alpha by delta t or d alpha by dt is nothing but the rate of change of the y velocity in the x direction, and similarly delta beta by delta t or db by dt is nothing but del of u by del y, or the change in x velocity in the y direction. We have just done these two proofs, if you may reiterate, in the last slide, okay, when we were trying to see the rotation of a component without deformation. This case there is a rotation and deformation simultaneously happening. Actually the rotation is happening because of the deformation of the two sides. All right. So essentially then this minus d gamma by dt, which is also d alpha by dt plus d beta by dt, would become same as del v by del x plus del u by del y. You may reiterate that d alpha by dt is nothing but limit of delta t tends to 0, delta alpha by delta t, limit of delta t tends to 0, delta neta by delta x divided by delta t, which is del v by del x, okay, and delta beta by delta t is nothing but the limit of delta t tends to 0, delta beta by delta t, which is equal to again the limit of delta t tends to 0, delta zeta by delta y delta t, which is nothing but del u by del y. Okay. So essentially here, mind you, this du by dy is positive, because if you look at the deformation, really the deformation here is in the same direction as the u here. So u was u0 here, and here it is u0 plus del u by del y times of del y. It is in the same direction as u. So therefore it is a positive addition. So therefore this is positive in this case, and thus the relationship 1 holds valid. Minus d gamma by dt is del v by del x plus del u by del y. So all said and done, we now have found out relationships of what would happen in case of a fluid element rotating by itself and a fluid element deforming by itself. So with all this knowledge in mind, and also the way we did the acceleration of a point vector in a fluid space, we combine all these things together to find out what would dynamically alter the cube as it moves along in such a flow field. Okay. There would be stresses, there would be principal stresses, there would be shear stresses which take place, and some of them we had illustrated in our last class when we were talking about the conservation of mass equation, where you will have sigma xx, tau xy, tau yx, tau zx as the three stress components because of the force in the x direction, and similarly three stress components, force in the y and z directions. So we had a stress matrix or a stress tensor that we defined in this manner. And so let us see that if all these things are individually implemented, and we can somehow find out the force by multiplying it with the area element of the different stresses, can we equate that to the mass of this cube into acceleration and find out what is the equation which is emerging from that. So this is essentially the conservation of momentum, right, Newton's second law. Rate of change of momentum is nothing but the force and takes place in the direction of the force. So we'll apply Newton's second law here that way and try to see what the final states of these relationships are between the different stresses, shear, principal stress, so on and so forth, the acceleration, the mass and the area elements. Okay. So let us look at our cube again, on the control volume again. You have a small cube which is of a volume dx. So this is x, y and z direction. So dx is the distance of this particular dimension of the cube, dz is the distance of this particular dimension of the cube, and dy is distance of this particular dimension of the cube. Okay. And so you have again different forces which are acting in the x direction. Let us say you have a force, let us just for the time being delete these arrows in the interest of space. All right. So we delete this, we by and large know what these dx, dy, dz are. So here we try to again do stress components. We have this component of stress. We assume that this cube is centered about a point O, where you have sigma xx, tau yx and tau, give me a minute here. So we have sigma xx, tau yx, which means due to a force x in the y direction, in the area vector is in the y direction, and tau zx. So at this particular edge of the cube or this particular face, okay, your stress components would differ. This would be sigma xx plus, let us say we have a variation in the x direction. So del sigma xx by del x times of dx by 2 would be the stress component in this face. The stress component similarly in the other face here would be sigma xx minus del sigma xx by del x times of dx by 2. Similarly the shear stress components that would be here and also in the opposite direction in the lower face would be, let us put this as a star, the star would be tau yx plus del tau yx by del y times of dy by 2 and tau yx minus del tau yx by del y times of del y by 2 or dy by 2. Similarly we will have the z components which are essentially in this face and the back side, and these components would be again, so these are double stars, del tau zx plus tau del tau zx by del z times of del z by 2 or dz by 2 and tau zx minus del tau zx by del z times of dz by 2 are the different components. Okay. So with all said and done, dfx therefore, which is essentially the total amount of force in the x direction, is as a result of all these different components. Okay. Component 1 here, 2 and these 3, 4 and 5, 6 all put together, and these are, mind you, all stress terms. So you need a certain area of cross section across which these stresses are applied in order to find out the net force on the particular cube of interest. So the net force in this case would be equal to sigma xx plus del sigma xx by 2 times of dx by 2, and the area vector here is dy dz, okay, dy times of dz as I had pointed out before. Okay. Similarly you have a stress in the opposite direction which is same as sigma xx, and here you have of course a minus del sigma xx by 2 times of dx by 2 times of dy dz. Okay. And similarly you have components related to the shear, and I will just try to illustrate this here as plus tau yx plus del tau yx by del y times of del dy by 2 times of dx dz, okay, minus tau yx minus del tau yx by del y times of dy by 2 times of dx dz. Okay. So, those these are the various components in the x direction, and mind you this tau yx again has a cross sectional area dx times of dz, that means this times of this. Okay. So, here you also have a third component of course as a part of the whole deal, where this tau zx plus del tau zx by del z times of dz by 2 times of dx dy minus tau zx minus del tau zx by del z plus dz by 2, I am sorry, into dz by 2 or multiplied by dz by 2 and times of dx dy, which is the cross sectional area. So, if I take a simplified form of all this, as you know here from this expression you can easily find out that the sigma x is actually really cancelled, because the dy dz are similar on both. Similarly, same goes true for the tau xy's, and only the differential components here are what is retained really, and similarly here tau zx and minus tau zx. So, what are the and if we assemble together all these different terms, then on simplifying we obtain d f sx is nothing but del sigma xx by del x plus del tau yx by del y plus del tau zx by del z times of dx dy dz as the total amount of the force in the x direction. Okay. So, therefore, you know, on a more simpler note, similar kind of expressions can be generated for the different force components in the y and the z directions as well, and let us just write this down here. So, in the y direction it should be sigma yy times of del y, okay, plus del times of tau xy by del x plus del times of tau xz by del z, all right, times of again dy dx dz, and similarly you have the other component here. It is really like a stress matrix. Okay. So, this comes here and this actually goes here. So, in the other component you have the del sigma zz with respect to del z, okay, and you have the component del tau of now you have the y component. So, this is actually zy, I am sorry, this is zy, okay, and so you have delta tau yz by delta y plus delta tau, you know, it is kind of xz by delta x as into times of dx dy dz as the three different components of the force. All right. So, if we involve the body forces at this stage and try to figure out what the overall would really look like, we will have this equation slightly modified, because we will then have to add the body forces along the x direction, the y direction, and let us call that dfxb, b for body, okay, dfby and dfbz, okay, as the different forces. And so, therefore, if we have all these different forces together, we will have to have and we can say that this is actually, you know, the body force Fb can be represented as the rho times of the volume, which is dx dy dz times of g, right, and g has three components again, gx, gy and gz. So let us write all these equations together in the next page. So the total force in the x direction because of the body force Fbx and the stress force, the force due to the stress vectors, can be represented as rho gx plus del sigma xx by del x plus del tau yx by del y plus del tau zx by del z times of dx dy dz. Similarly dfy is again having a body force in the y direction plus a stress force in the y direction, which can be rho gy plus del tau xy with respect to x plus del sigma yy with respect to y plus del tau zy with respect to z times of dx dy dz, and dfz is equal to del body force in the z direction plus stress force in the z direction, which can be rho gz plus del tau xz by del x plus tau d tau xy by dz dy plus del tau or del sigma zz, because it is not a shear force, there is a principal stress, sigma zz by del z times of dx dy dz. So these are really the equations for the total forces that the control volume CV would encounter due to stresses as well as its own weight in all the three directions. Okay. So this kind of brings us to an end of this particular lecture. So the next lecture, what I would like to illustrate is that we move ahead with this this force equation and try to kind of compare it with mass times of acceleration and see what the final form of equation would be like. Thank you.